Welcome to this explainer. If you've ever stared at a classical mechanics textbook and felt totally overwhelmed by the sheer mountain of equations, trust me, you are absolutely not alone. It's so easy to get bogged down in the algebra and completely miss the incredible story it's trying to tell us. So today, we're going to reframe things. We're not looking at mechanics as some messy, disconnected pile of formulas you just have to memorize. Instead, we're going to see it for what it truly is, a beautifully cohesive language, spoken in three distinct but perfectly complementary dialects. By the end of this, you're going to see how what looks like pure chaos is actually just an incredibly elegant system for decoding our universe.
And the magic number for us today? It's 3. Literally everything you see around you when it comes to macroscopic motion, whether that's the simple, lazy arc of a tossed baseball or the incredibly complex, majestic planetary orbits dancing through our solar system, it all boils down to exactly 3 interconnected pillars. Once you master these 3 pillars and really get how they speak to each other, you basically hold the master keys to analyzing the physical world.
So here is our roadmap for today. First, we'll look at kinematics, which is the how. Second, Newton's laws, the why. Third, energy, the constraint. And finally, we'll pull it all together into a unified framework. Let's jump right into part 1, kinematics, describing the how. Think of it this way. If classical mechanics were a movie, kinematics would be the camera. It acts as this pure, totally unbiased observer of the universe, just recording and predicting the geometry of motion as time takes by. Kinematics focuses solely on how objects move. It genuinely doesn't care at all about the invisible pushes or pulls that cause that motion to start or stop. It's strictly dealing with position, velocity, and acceleration. If you know a dropped ball's current state and its constant acceleration, say the gravity right here on Earth, kinematics gives us the exact mathematical framework to predict precisely where that ball is going to be 3 seconds from now. It's pure, unadulterated forecasting. Okay. I know these 4 core one-dimensional equations can look a bit intimidating at first glance, but really, they shouldn't be. Instead of just reading them as this random alphabet soup of variables, try to think of these equations as a story. They're the mathematical tools that let us perfectly map an object's entire trajectory over time. And notice what's missing here: force, mass. These equations map the journey without ever once asking what gave the object a shove in the first place. But to truly understand motion in its entirety, we have to shift gears. We have to transition from the passive observer of kinematics over to the active instigator of dynamics. We need to figure out what actually initiates that change in velocity. Simply put, we need to know the why. Which brings us to part 2, Newton's laws, the why. Formulated way back in the 17th century by Sir Isaac Newton, these profound laws finally gave humanity the power to explain the fundamental causes of motion by directly linking them to forces. And Newton didn't just hand us one rule, he gave us a rhythm of 3 foundational rules that perfectly govern exactly how forces interact with mass. The first law defines the natural state of things, the second quantifies the changes to that state, and the third dictates the rules of engagement when multiple objects interact. Let's break them down real quick. Newton's first law introduces this beautiful concept of inertia. Basically, an object just wants to keep doing exactly what it's already doing. So the absolute crucial point here is this. In the absence of a net external force, an object's acceleration is strictly 0. If it's sitting still, it stays still. If it's coasting through the vacuum of space, it's going to coast forever at the exact same speed and in the exact same direction. And hey, notice how this perfectly aligns with that kinematic case of constant velocity we just talked about? You see, the dialects are already starting to translate one another. Then we get to the absolute crown jewel, Newton's second law. Force equals mass times acceleration. F equals ma. This equation right here is the ultimate bridge. It acts as a direct translator between our first 2 pillars, quantifying exactly how a push or a pull, a force, translates into a physical change in speed. Once you use the forces acting on an object to compute its acceleration, you can take that A, turn right around and plug it back into our kinematic formulas to predict the future. It's an incredibly powerful feedback loop. And then the third law completes the set by explaining interactions. You literally can't touch something without being touched back. Think of a massive rocket launching into space. It violently pushes exhaust gas backward, and as a reaction, that gas pushes the rocket forward. But a super critical thing to remember here is that these paired forces are acting on different bodies. That is exactly why they do not just cancel each other out to 0 for a single object. Moving on to part 3, energy, the ultimate constraint. Now we meet our third and final pillar, which I personally like to call the accountant of the universe, energy.
Now, while forces and kinematics deal with the gritty, moment-by-moment details of a journey, energy steps back and gives us the grand, overarching rulebook. The law of conservation of energy dictates that in an isolated system, the total energy must remain perfectly constant over time. The universe, it turns out, is a very strict bookkeeper. Energy cannot be created from absolutely nothing, and it cannot be destroyed. It can only be transformed from one form to another, kind of like transferring funds between different bank accounts. This gives us a wonderfully powerful alternative to integrating complex forces over time. Because if only conservative forces, like gravity, are doing work, total mechanical energy is always, always conserved. Just imagine a swinging pendulum. At the very top of its swing, it completely stops for a fraction of a second, right? At that moment, all its energy is stored up as gravitational potential energy. As it falls, it speeds up, continuously cashing in that potential energy for kinetic energy, the energy of motion. At its absolute lowest point, it's moving its fastest, meaning kinetic energy is totally maxed out. But the beautiful part? No matter where that pendulum is in its arc, the sum of those two values remains perfectly, flawlessly constant. And finally, part 4, a unified framework and how all these interconnections work. Having zoomed in on our 3 individual pillars, it's time to step back and see how they actually form direct bridges to one another. They create a completely unified framework. If you want to connect Newton to kinematics, well, F equals ma provides that acceleration variable you need. If you need to connect Newton to energy, you pull out the work-energy theorem, where the work done by forces equals the change in kinetic energy. And if you want to skip forces entirely and jump straight from energy to kinematics, energy conservation gives you a brilliant shortcut to find velocities without ever having to worry about complex differential equations involving time. It's just this perfectly interconnected web of logic. Which naturally brings us to a pretty crucial question. Do all these methods actually agree? Like if we use kinematics and forces, will we get the exact same answer as if we asked the energy accountant? To prove the absolute consistency of the universe here, let's apply all 3 frameworks to one classic physics problem: a block of mass m sliding down a completely frictionless incline of height h. So on the left side here, we're taking the scenic route using forces and kinematics. We have to resolve gravity into angles just to find our acceleration. And then we use trigonometry to find the actual distance traveled along the ramp. Then we take both of those and plug them into our kinematic equation. Now, on the right side, we use energy conservation. We simply equate the initial potential energy at the top of the ramp to the final kinetic energy at the bottom. The right side definitely looks a whole lot simpler, but do they actually lead us to the exact same destination? Oh, absolutely. Both methods collapse down into the exact same elegant result. Velocity equals the square root of 2gh. Whether you meticulously track every single force and angle moment by moment, or you just balance the universe's energetic checkbook from start to finish, classical mechanics proves itself to be a perfectly coherent system. The math literally never lies. As our source material wisely points out, these approaches must always yield consistent results. If you're ever working through a real-world problem and your energy calculation completely disagrees with your kinematics calculation, well, it signals an error in your assumptions. It usually means you missed a friction force somewhere or maybe misidentified an angle. It definitely does not mean the fundamental rules of the universe suddenly broke. And that leaves us with a final thought on the sheer elegance of physics. By fully understanding kinematics, Newton's laws, and energy conservation, we can transform what once seemed like random and intimidating formulas into a single master key, a key capable of unlocking exactly how our universe operates on a macroscopic level. So I'll leave you with this to ponder. Is the universe simply one giant, elegant equation just waiting to be balanced? Thank you so much for exploring the mechanics of our world in this explainer. Keep questioning, keep learning, and I'll catch you next time.